Hi everybody, today we're going to talk about the binomial option pricing model. Okay, so what is the binomial option pricing model? Well, suppose we are here at t equals 0 and we have a stock. It has initial price 100, okay? And in this model, at t equals 1, the stock can only go two places. It can only go up to 107 or it can go down to $93.46, okay? Now at t equals 2, the same thing happens. It can either go up to 107 times 1.07, or it can go down back to 100. Okay, and same thing happens from this situation. Okay, 93.46 divided by 1.07. And all of these movements happen with probability, so it goes up with probability p and down with probability 1 minus p. And this is true for any of these arrows. Okay, so this is binomial in the sense that from your current spot, you can only move in two places, and the distribution that you end up with at the end is a binomial distribution, right? It's much more likely that you end up somewhere in the middle than winning twice or losing twice, for example. So it follows like the Pascal's triangle distribution. Okay. So the question is, given this model of an underlying stock, how do you price an option, a call option? How to price a call option? So the call option, you opened it at t equals 0. Sorry, t equals 0. It expires at t equals 1, and it has a certain strike price k. Okay? So let me give you an example. So if the strike price is the initial value, so if k is S0, okay, then at t, if your call expires at t equals 1, then you make here 107 minus $100, that's your strike price, so you make $7. And then in this case, if it goes down to 93.46, then you make 0. So this is a, so these are the two possible situations that might happen. And in one case you make $7, in the other case you make 0. So how should you price this option? Okay. Okay, so let me give you some more simple examples. So what if the strike price is 107, right? So if the strike price is 107, then in both situations you make 0. Therefore, your price of the option should probably be 0. So in the case, if it goes up to 107, you hit the strike price. So you don't get anything out of it as t minus k. And if it goes down, you don't exercise the option, so you still make 0. Okay, so another example, what if you, this one is a little bit more difficult, what if the strike price is 93.46? So in one case, you make 107 minus 93.46. In the other case, you make 93.46 minus 93.46. So this is not 0 anymore. So how do you price this option? In either case, you make S1 minus $93.46, right? So what is a value, what is the price of a cash flow, of a guaranteed cash flow that's equal to this? Well, a way you could replicate this with a portfolio is you could you could buy stock. You could buy S0 at t equals 0. So you buy 1 unit of the stock, right? And then you borrow 93.46 divided by R, where R is the interest rate. It's written like this, 1 plus R, where R is, our usual understanding of interest rate. R is just the version of it where it's greater than 1, so like 1.05. Okay, so you borrowed this amount of money, and now, so you've constructed if it makes sense, a replicating portfolio. So you bought some of the stock, you borrowed some money, and then at time equals 1, the things that you did at t equals 1, they sort of transform, and now you can sell a stock at S1, and you have to give back 93.46. So this is exactly the price of entering into this. So the price of entering into this call should be S0, right? Like I said, minus 93.46 divided by R. So hopefully that makes sense. So, however, what happens if the strike price is in between? Is here is in between 93.46 and 107. Okay. So now you might be interested in the possibility of, since you're looking at it, you're thinking, oh, it's a binomial model. I know the probabilities. With probability, it's going to, the probability of it being here is p squared, right? So the probability of ending up here is p squared. The probability of ending up here is 2 times p times 1 minus p, because there's two possible ways of getting here. And the probability of this is 1 minus p squared. I should just take the expected value of it, discount it. So, idea. So what if it's just this 1 over r multiplied by the expected value of sort of C1, if that makes sense, the future cash flow, which should just be, over all the possibilities, right? Or in this case, I did 2, so let's say we're discounting it over r squared instead. So this should just be p squared multiplied by so this will be the price of the stock, so 107 times 1.07 minus the strike price K, right? And then plus 2p, 1 minus p, then 100 minus the strike price K. And then, it depends on what the strike price K, like let's just say, if the strike price is 100, then you get nothing if it hit this bottom one, right? 93.46 divided by 1.07. So then you take this, so this would be the expected value, and you could happily compute it like that. However, this is not actually what is used to price options. I think one difficulty with this approach, as described by the professor, is what if you care more about, there's an example he gave, which is called the St. Petersburg paradox. So suppose you're playing a game and it gives you, basically you're flipping coins, okay? So, and if the coin lands on heads, so you're looking for the first time that the coin lands on heads. So if it lands on heads at the first time you flip it, then you get $1, okay? And then if it lands on heads for the first time on the second time, then you get $2. And then next time you get $4, and next time you get $8. So the expected value of such a game, I'll just write of the game, okay, is the sum of the probability. So the probability of it landing the first time, let me remove the sum for now. The probability of it landing the first time is 1/2 on heads, and you get a payout of $1, right? And then the probability of it landing on sort of heads the second time is 1/4, right? Because it didn't land the first time, but it landed the second time. So that's 1/4 multiplied by 2, right? Plus 1/8, right? Multiplied by 4. So then if you notice, this is just the infinite sum of 1/2, which is infinity, right? So the expected value of this game is actually infinity, even though the probability of hitting, increasingly larger amounts of cash, like the probability of winning $1,024 is 1/2000. What is it? 1024, 2048, right? So the question is, how much would you value playing this game? And the answer might be not a lot, because even though the expected value is infinite, the chance of you getting there is so tiny that maybe humans are risk averse, so maybe it's not worth to go in that direction. Um, so that's why it might not be a good idea to price options using the expected value, because maybe you care more about losing than you care about winning. And so it doesn't really balance out. So now you might be thinking, okay, maybe we need a utility function like a log function, which sort of smooths it out, right? So that winning a lot, like basically you care about like the difference between, like you care about utility functions are whatever, I think they're concave. The point is they look like this. So winning a lot in the beginning matters a lot, but winning increasing amounts, so this is win and then this is your satisfaction. So winning increasing amounts is not as nice. Is not as rewarding for you, right, as a human being. But it turns out that we don't even really need this either to price options. What we need instead is the following. Well, okay, actually, I'll get to that in another lecture. How to price options using replicating portfolios. Okay, thank you so much. See you next time.